ARM. One of the only two surviving CPU architectures in use in general-purpose computing on any significant commercial scale, with Apple recently moving the Mac over to ARM, and large-scale cloud providers like Google and Amazon shifting over to it as well. It might well become the CPU architecture that's dominant in pretty much every major space. But ARM has a particularly interesting history, which is what this video is going to be all about. Yes, we're going to look at ARM's origin story, which is where most videos on this begin and also end, and we'll also look at some of the other major events that have shaped ARM. You know, the bits that happen after the origin story that are equally as important to shaping the ARM we have today. Welcome to the potted history of ARM. Well, after you've had a quick word from our sponsors. The sponsor of today's video is PCBWay. So close. A company that, wait for it, makes PCBs. How could you still see that coming? They also, in a more surprising twist, do things like 3D printing, injection molding, CNC machining, and, maybe slightly less surprisingly, pick-and-play services for basic components to go on your PCB as well. And of course, they sponsor YouTube channels like this one, so we can bring you nice and interesting videos about things like the ARM processor. Speaking of which, like all good superhero stories, you gotta have a decent origin myth. And very few CPU architectures have an origin myth as good as that as ARM. It's like the Iron Man of CPU origin stories, only, you know, with less caves and explosions and CGI. It's also why a lot of videos that cover the history of ARM also do the origin story and then ARM was a massive success and, you know, phones. So it's now my turn to do the origin story. And it's going to lay down one of the key important things that would later on go to make ARM a massive success, but it doesn't happen for the kind of reasons you think it might. Sitting between the Gap and Oasis clothes stores in Cambridge, you'll find a little alleyway, and if you happen to go through that alleyway, you will find yourself at the door of 4A Market Hill, once the offices of Acorn Computers, a then still relatively small computer company which was recently starting to have a lot of success with its new product, the BBC Micro. The two main designers of the BBC Micro were Steve Ferber and Sophie Wilson. That's not to say that there weren't lots of other people involved in getting the BBC Micro from an idea they had to a thing that they could produce in production and sell, but Steve and Sophie are the two who get the main credit for designing the machine in the first place. Whilst both of them still had a lot of other work they were doing at Acorn, Sophie had been toying with the idea of an instruction set for a RISC processor. Given Sophie had written BBC Basic and a number of other bits of the operating system for the BBC Micro, she had a fairly good idea of what you might want out of a low-level instruction set for a CPU. A number of events then coincide to go from toying around with the idea of something to actually getting to the point where you might consider as a business building a CPU. Now, the BBC Micro was based around the 6502 8-bit processor, a chip designed in the 1970s by Chet Peddle team at MOS. While in the early 80s this was pretty good as an 8-bit microprocessor went, but everyone knew the future was not exactly going to be 8-bit. So, Steve Ferber and Sophie Wilson flew out to Arizona in the States to the Western Design Center, a company that was then working on a successor chip to the 6502 that was going to be 16-bit and have 24-bit memory addressing, and would eventually become the main processor for the Apple II GS. The 65C816. As a potential processor for a next BBC, it had a lot of advantages to it. It was compatible with the 6502 they were already using, so a lot of existing code was going to run. In fact, there was even a 40-pin version that could work as a slot-in replacement for the existing 6502. With all this in mind, you can see why both Sophie and Steve thought it was a good idea to fly out to WDC. Now, before going, they had an image of the Western Design Center in their head, which is very big, corporate, American, high technology. When they got there, yeah, that didn't quite match up to the reality. What they discovered was it had much more of a cottage industry feel than they were expecting, with the design work for the new chip being done in some random house in the suburbs. Now, this was much more akin to Acorn setup, which meant that when they returned, they realised that there was not the capability gap that they thought there was between themselves and WDC. They also were not wildly impressed with the new chip WDC was working on, particularly Sophie Wilson, it would seem. She was very much under the impression that they could do a better job. And, to be fair, she was proved right. Now, two people visiting a random company in the States would probably not be enough to persuade Acorn to suddenly shift focus onto CPU design, but some other things were happening that coincided at the same time that pushed Acorn down this route. Herman Hauser, one of the main directors of Acorn, had been talking to Andy Hopper, one of the people involved in the Cambridge Ring, and who'd also given Acorn the initial idea for Econet. In this conversation, Andy had told Herman in the future there'll be two kinds of computer companies, those who are involved in silicon and those that are dead. Herman decided he wanted to be the former rather than the latter, and thus part of Acorn's strategy had become to get involved in silicon. So they'd staffed up with a number of engineers and also bought themselves some pretty expensive Apollo workstations to run their silicon design tools on. This meant that Acorn had a capability of doing silicon, but didn't yet have anything to do with that capability. And suddenly, here's Steve and Sophie returning from their trip with an idea of something that they could do with their silicon capability. The timing on all of this is basically perfect. If this had happened at a different time frame, that silicon design team could have already been busy, or the capability may not have been in place, or maybe there wouldn't have been the trip that made them realise, yeah, this was well within Acorn's capability range. But with the timing being the way it was, Acorn decided to go ahead with its very ambitious project. So in 1983, two major projects began. Project A, which would become the ARM microprocessor, and Project B, which would eventually become the BBC Master. In terms of the split of the engineering duties between Sophie Wilson and Steve Ferber, Sophie Wilson worked on the instruction set for ARM, whereas Steve worked on the higher level electronic design. Now, one of the major goals given to Steve was that they wanted the new CPU to be able to go into a plastic package, rather than a ceramic one. The main reason being for this, if you want to package a CPU in plastic, that costs fractions of a cent to do per chip. If you have to use a ceramic package on the other hand, well, that becomes tens of dollars per chip. This is a huge increase in unit cost per processor, so very much it would have worked in Acorn's favour if they could get it into a plastic package. Now, as many of you out there will know, if you want a low temperature device in the world of electronics, that means you need to use less power. So the new ARM processor was going to have to be pretty energy efficient. Now, energy efficiency in itself, not a goal here, but staying within a particular thermal envelope meant that they needed to consume 1 watt or less. Now, this decision to stay within the 1 watt envelope for the plastic packaging would be fateful to the future success of the ARM. As much of the success of ARM in the future depended entirely on the fact it was an extremely energy efficient processor, as it was used in a lot of applications where you didn't have a lot of power that you could consume, i.e. mobile applications. But in 1983, nobody's thinking about mobile use. The exact timings of what happened between 1983 and 1985 when they got the first ARM samples back is a little bit muddy to say the least. I can find a number of written accounts of what's happened and they all conflict a little bit in terms of dates and times, but that's not that surprising as a lot of things were happening in Acorn between 83 and 85. The BBC Micro had become a huge hit for them, and that meant that Acorn needed to change quite a lot as a company. Firstly, it got itself a much bigger premises at Cherry Hinton, but also it hired itself quite a lot of staff, because at one point, everyone who worked at Acorn didn't actually work for Acorn. Almost everyone seemed to be a consultant working on a little thing here, a little thing there, using it as a way to start their own thing that they were going to do. So, for example, Kim Spence-Jones, who did all the work on the board for the BBC to get it production ready, didn't actually work for Acorn. He was a consultant and in fact went off to go start SJ Research. Even those who were considered Acorn employees like Steve Ferber and Sophie Wilson, technically, they didn't work for Acorn, they worked for CPU Limited, which is like a consultancy company that was run by Chris Curry and Herman Hauser, who were also the directors of Acorn, that had effectively become the holding company for Acorn Computers itself. You also have a lot of things going on with product development. For example, in 83, Steve Ferber kept getting pulled into sorting out the problems with the ULA for the Acorn Electron, a product that was fairly late and did have some big financial implications for Acorn. You also had stuff going on with the Acorn Business Machine, or ABC, that eventually would become the Cambridge Workstation and would, how do we put this politely, suck? You also have them trying to get the BBC into the US, or as my friend calls it, the PBS, which was a whole adventure story in and of itself. And if all that did not seem like quite enough, the 83-85 windows when they start working on the BBC Doomsday system, which is probably the most impressive thing anyone ever did with an 8-bit micro. So, given the muddiness of the timeline, I'm going to jump to 1985, when they have finished and taped out the design of the ARM processor, jumped on a plane, taken it to Munich, where they could run the final design checks, because of course Acorn did not have the toolset to do that, remember, cottage industry. And finally, the first engineering samples of the chip had been produced by their new silicon partner, VLSI Technologies. Now this is where I get to tell you about a great ARM tradition, that of the champagne. Herman Hauser bought 2 bottles of champagne, ready to celebrate the moment they got their first chip to work. So, on the 25th of April, 1985, when the first ever engineering sample of the ARM processor arrived at Acorn, it was eagerly plugged into the PCB they had ready and waiting for it, which had been designed to run the ARM and connect it to a BBC micro using the tube port, which is a feature of the BBC that allowed you to add a second processor to the computer. Unfortunately, on first test, it didn't work. Not exactly surprising. But apparently after 2 hours of fiddling around with the PCB and sorting it out, they were able to fire up the copy of BBC Basic that they'd written for the ARM processor, while still not having an ARM processor, and on the screen of the BBC appeared the words, "Hello world, I'm an ARM," which of course meant it was time to break out the champagne. Now this is a tradition ARM has kept going ever since, so whenever they get a new chip back and it works, the champagne gets opened. All the champagne bottles for the early ARM CPUs are all held in the collection for the Centre of Computer History. I'd love to show you a photograph of them, but unfortunately I can't find one. Now after a day or two of doing testing on this new ARM chip, Steve Ferber decided it was time to measure how much power the thing was consuming. After all, they did have to stick within that 1 watt range. Well, after connecting up the multimeter, he was quite surprised to discover that the chip used 0 amps were being pulled by the power supply line. Which, as you can imagine, initially surprised Steve quite a lot, to discover that actually, all this time he'd been using it, he didn't have the power supply connected to the chip. What had been going on all this time is the power protection diodes on each of the inputs inside the chip had actually been powering the chip all along. So after getting the chip connected up to a power supply so it wasn't just scavenging power from its input lines, they could measure how much the chip was drawing, and it consumed a grand total of 0.1 of a watt. Yes, it actually hit their target by more than an order of magnitude. Now the way they got there isn't just some form of special Acorn magic. It's all about keeping the transistor count low, because that's where power gets used in a chip when a transistor changes state. So the less gates that you have, the less power you're going to use. So the first ARM had around 25,000 gates in it, which may not sound like the smallest of numbers, but the 386, for example, had 256,000 gates in it. You know, that's at least 10 times more. That's why the 386 was in a ceramic package, while the ARM chip could be in a plastic one. The first version of the ARM chip released to the public was again an ARM1, on a board that you would connect to the tube of the BBC Micro, known as the ARM Evaluation Kit. The idea of this thing wasn't so much to just make a more powerful BBC, it was for software developers to be able to get their hands on the ARM and get to grips with it and have software ready for whatever machine that Acorn was going to release. In order to get to the point where they could release a machine, they needed to develop some other chips as well. After all, a computer's a bit more than just the CPU. So ARM developed MEMC, VIDC, and IOC, which handled in turn the memory, the video, the I/O. Around this chipset they developed 2 new machines, the A310 and the A305, which were both initially branded up as BBC, but as the BBC branding deal started to come apart, it was later all rebadged as the Archimedes range. Now design didn't just stop with the ARM1, they in fact went on to develop the ARM2, which is what they used in the Archimedes machines, which was a bit more advanced than the original ARM1. In particular, they did some work around multiplication, and also what's known as fast interrupt request mode. If you want some idea as to how fast the ARM2 was that shipped with these Archimedes machines compared to other machines at the time, so if we compare it to a 7MHz 68000, the sort of thing that they shipped inside the Amiga 500 and the Atari ST, well, it was roughly 7 times faster than that. It was about twice as fast as a 386 clocked at 16MHz. So the performance of this thing was good. I mean, really good for its price point. But all while this is happening, ARM is essentially still just a design group inside Acorn. That's until 1990, when Acorn takes the decision to spin ARM off into its own company. And the company was known as Advanced RISC Machines. That's where ARM stops meaning Acorn RISC Machine and starts meaning Advanced RISC Machine. We're now at the point of our tale where we can say that the origin myth is now complete. We now have the modern ARM company, and this is where most videos then say, and they went on to be really successful in the mobile phone market. The end. But actually, there's quite a few things that happen between where we are now and getting to the and then they were really successful the end. There's about 3 or 4 major events I still want to look at in the history of ARM. And the first one we're going to look at is the Apple Newton. If you remember the Apple Newton at all, you'll either think of it as something that was far too ahead of its time to succeed or actually be of a lot of use, or there'll be that handwriting joke from The Simpsons. The Newton was Apple's first attempt at a PDA, a personal digital assistant. It was the sort of thing we used as a mobile computing device before, smartphones and tablets were a thing. Now, in many ways, it's not that dissimilar to a smartphone. It doesn't have a cellular modem and can't connect to anything else, or at least not without attaching external equipment. But you had a touchscreen, you had a pen you could use that did some sort of handwriting recognition. Yeah, that part was kind of rubbish. It's battery powered and could fit in the pocket, and you installed apps on it as well. You can definitely see this class of device as a forerunner to the smartphone. But the big thing it was that it was battery powered. And battery powered meant that you needed a very power efficient microprocessor to go in it. It was also very limited in terms of its RAM, so you also needed something that was very code dense as well. Now, initially the Newton project had gone completely off the rails, so Apple turned the reins over to Larry Tesler, who, when looking at what they developed so far, decided that they needed to dump the CPU that they were using and find something somewhat more battery friendly. And the company he turned to was Acorn Computers and their ARM processor. Now, as mentioned before, the ARM processor was really power efficient to be able to stay in that plastic packaging, but suddenly, the power efficiency mattered for battery life, which meant that the ARM was a natural for this kind of application. Also, they added something really useful to the ARM processor, known as thumb mode. This is essentially where you can only address a very limited amount of memory and use a much smaller instruction set, but it makes that code handling very, very rapid and compact because you're only using 8-bit instructions, but it also means you can turn off a big chunk of the CPU, which saves even more power. This relationship with Apple and the Newton had two major effects on the ARM processor. First of all, it gave them a whole new idea of a business model, that of licensing their chip out for other people to use it. The ARM didn't just have to be stuck in machines made by Acorn. The second was also, do you remember I mentioned when they sort of spun off ARM into a separate company in 1990? Yeah. Well, Apple was a very big influence on that. Essentially, Apple didn't want to buy from a small supplier in the UK that had some financial troubles in the past. So ARM was spun off into a company that was part owned by Olivetti, who essentially invested in Acorn Computers, and also by Apple themselves. Now, eventually Apple would go on to sell their share in ARM, and that was one of the things that managed to keep Apple in the black when they were having significant financial troubles in a few years' time. But the Newton transformed ARM's business model and gave it an entirely different way of dealing with the world. ARM could now be about licensing its intellectual property. It wouldn't necessarily produce whole CPUs. It would allow someone to borrow their IP, include other bits of IP around it, so you get a chip with essentially a processor and a whole bunch of other system components on there, which is basically how ARM makes all its money today. However, this change of business model didn't exactly bode well for Acorn the computer company. At some point it became true that essentially Acorn the computer company was holding a value of shares in ARM that was worth more than Acorn the computer company, so if you wanted to buy ARM, the most cost-effective way to do it was to buy Acorn. So this is a situation that couldn't stand, and the shares in ARM were transferred to the shareholders of Acorn, and Acorn the computer business eventually shut down, becoming, I believe, Element 14, which later got sold to Broadcom. And that's the bit of Broadcom that's responsible for the Firepath processor, as that's where Sophie Wilson ended up working. Now, if you find yourself thinking, I've never heard of the Firepath processor, well, while you may not have heard of it, you've definitely used it, as Firepath is very heavily used in DSL equipment. Not necessarily in the modem that you have in your house, but the exchange equipment, well, virtually all of that uses Firepath, it seems these days. Now, the next part of ARM's history I want to look at is the strong arm. This is another one of these shifts in the business model for ARM, and also being an interesting technical update to ARM as well. Now, so far through the Newton, Apple have licensed a complete CPU core to someone to include on die for another device, i.e. the Newton. This was a different type of licensing. What ARM were going to license out here to DEC was the instruction set. So, in the case of strong ARM, none of the actual hardware design is being licensed here. None of the CPU architecture, etc., none of that stuff. It's just the instruction set. What DEC were planning on doing was implementing their own ARM CPU and designing all of it themselves. They just need to license the instruction set from ARM so they could be compatible with, well, ARM. Now, DEC is a company that had a long history of designing their own CPUs, all the way back to their PDP range, which is essentially a very large hand-assembled CPU with transistors, all the way through VAX, and, at this point in time, their latest CPU, the Alpha. For them, ARM was going to fill a nice niche, essentially for a small, energy-efficient RISC processor that they could include in various devices, not necessarily computers, but they could embed it in the likes of a RAID controller, they could put it in a laser printer, wherever they needed a CPU to replace a big pile of logic. For ARM, this was also a really big deal. At the time, DEC was the second largest computer company in the world, second only to IBM. And from DEC's standpoint, licensing a CPU instruction set meant they didn't have to create all their own compilers, tools, a lot of stuff that goes around the CPU, including, most importantly, something they were supplied by ARM, the test suite. When developing a CPU, you're not just developing the processor itself. You have to develop a whole bunch of tools to test that processor out to check that it actually works. Or at least if you have half a clue, that's what you need to do. Somehow I think this point may have slipped by in Intel in the late 80s, early 90s, and they forgot to test some of the floating point functionality of their Pentium CPU. And it turns out, it didn't do maths quite how maths should be done. Anyway, back to ARM. When DEC licensed the instruction set from ARM, they also licensed ARM's test suite. This meant when they designed their own chip, they actually had a test suite they could run it against to discover had they got anything wrong in it. Now this test suite was fairly ramshackle, should we say? Bits of it had been written on a BBC Micro in hand assembler and, they'd lost the source code for bits here and there, etc. And also that test suite had never been run outside of ARM before, because this is the first time they were licensing the instruction set out. So when DEC were testing their chip for the first time, they discovered some of the more, let's say, terse error messages that were in there. This actually created quite a to-do between DEC and ARM, as DEC regarded one particular error message that was surprisingly terse as, well, a little unprofessional, let's put it that way. This led various people at ARM to find out who the heck had put this terse error message in there. To which they found the answer was Hugo Tyson. Apparently the call went around ARM that Hugo needed to come in and speak to their managing director to be told that Hugo doesn't work here. In fact, Hugo never worked at ARM. Hugo used to work for Acorn. Viewers of this channel may be familiar with Hugo Tyson as the creator of Acorn's ADFS, the Advanced Disk Filing System for the BBC Micro, who, like almost anyone who could write any code in Acorn, have been pulled into helping write a bit of test code for the ARM. Now, Hugo's excuse for the terse error message is that memory was limited, so you can only use small amounts of text to describe something. So, when a particular other processor, let's say, messed up? Yeah, we'll go with that. You just implied that particular bit was messed. Despite these little hiccups, Strong ARM went on to be quite a successful version of the ARM, to the point where even Acorn adopted it as an upgrade CPU for their RISC PC line of machines. And DEC had also introduced some pretty good floating point support into the ARM. And a weird twist of fate, this part of DEC would end up getting owned by Intel of all companies, meaning that Intel became a licensee of ARM. In fact, Intel went on to sell Strong ARM processors for a surprisingly long amount of time and then changed the name to Xscale for a while. This brings us on to the final major thing I want to bring about on the history of ARM: testing. One of the things the deal with DEC highlighted was the importance of testing to ARM. After all, if you're going to license blocks of IP to other companies, that stuff needs to work. They need to be able to rely on you. So from ARM's point of view, they need to make everything provable. Now this is where the influence of Professor Mike Holcomb from University of Sheffield comes in. One of Professor Holcomb's main areas of study at the time was that of software testing, and as one of the leading academics in that field, he was a fairly logical choice for ARM to start talking to. And it was Professor Holcomb that persuaded ARM it might want to consider setting up its new testing division in Sheffield. This was quite a departure for ARM, as up until this point, pretty much everything to do with ARM had been based in Cambridge. But with a ready pool of graduates all trained and ready, ARM opened its new offices up in Sheffield, where its testing and verification group would live. Now, initially just a small office, above some shops on West Street, after a few short years and a couple of excellent Christmas ceilidhs, this group would expand and relocate to other premises, and then expand again, and again, and again. I'm told by various ARM staffers that ARM Sheffield is now the biggest single office of ARM these days. Although I can't verify that independently because ARM unsurprisingly does not publish headcounts and offices. Now, a huge part of this is the continual expansion of the verification and testing group, as that has essentially become one of the most important functions within ARM. If you're an ARM licensee, what you are getting is essentially a guarantee that this stuff works and has been tested, and also a test suite that you can run with the stuff that you integrate into the chip. If you're an instruction set licensee, well then you have a full test suite to test your design out. This is one of the huge selling points of the ARM instruction set, or if you're licensing the architecture, the ARM architecture. Other small IP cores exist that you can license, but they just don't come with the same level of testing and verification. And if you're going to spend a lot of your money designing your product around something like this, you really need to know that it works and have the test suite to prove that your stuff around it functions too. As this saves you a huge amount in terms of man hours, and any failed chips are really expensive because making the mask to produce silicon is hugely expensive. You want to do that once. I mean, when we talk about ARM, we tend to talk about all the exciting things like clock rates and big cores and little cores, and getting a new kind of memory controller so it can do DDR whatever it is now. The testing side of things just gets ignored. People don't talk about that because it's not super exciting. But the testing is equally a part of ARM's success as all the other things like your big cores, your little cores, and all the design work that goes into it. If you're the actual manufacturer that uses this stuff, then testing, well, almost matters more. Now, I don't want to leave you with the impression that the Sheffield office is just verification and testing. There are actually other things that happen there. Largely this is because at some point, ARM let people decide if they wanted to work in Cambridge or they wanted to work in Sheffield, and we're happy with them to relocate, and quite a few did relocate out of Cambridge. Now, I know what you're thinking, Sheffield, that doesn't sound as glamorous as Cambridge, right? But there are a lot of good draws into the Sheffield office. And one of the major ones is the disparity in house prices. For example, if you owned a 1950s semi-detached in Cambridge, you could sell it and buy yourself a small Victorian mansion in Sheffield, and more or less wipe out your mortgage into the bargain. So you can see why quite a lot of Cambridge people thought, I might go live in a larger house somewhere else and not have a mortgage. And also, in Sheffield, a lot of the more esoteric hobbies of ARM staff in Cambridge, well, they were available in Sheffield with bells on. Whew, even for me, that's an obscure joke. That about hits the point where I've discussed all the things in ARM's past I want to talk about that have got ARM from two people in Acorn saying, I have a cunning plan, to the massive successful company that we know today, whose processor designs the majority of you are using to watch this thing on. So you may be wondering, what does the future hold for ARM? Well, let me get out my crystal ball. Hang on a second. Now, ARM is no doubt going to continue in the space that it has been for all these years with these small, energy-efficient processors in mobile computing devices like smartphones and tablets. But also, of late, they've started to get into the high-end server market as well. Data centers are all about getting as much compute as they can get for the number of watts outputted and the heat density. And here, ARM has a great advantage over the likes of Intel, and they've not been afraid lately to push that advantage. I mean, with the likes of Google and Amazon getting processors directly from ARM themselves now, all the big providers of compute are starting to move in ARM's direction, and this could become a potentially huge market for ARM going forwards. We've also seen on the desktop they're making a lot more inroads lately. Yes, from the space that Acorn was forced to retreat from, we now have a number of Chromebooks that use ARM CPUs. All of Apple's laptops now use ARM as well, as do their desktop machines. Yes, the Mac platform has moved on to its fourth and possibly final CPU architecture, ARM. But all is not necessarily rosy in the ARM garden. I mean, there are threats, things like RISC-V, which is essentially an open hardware CPU architecture. That's becoming bigger and bigger and starting to get used in projects, and it's starting to get into the bottom end of ARM's market. Of course, it doesn't come with all the testing and verification in the same way that ARM stuff does, so until RISC-V gets there with that stuff, their growth in that market may be a little bit limited. There's also a question mark hanging over the ownership of ARM. ARM's currently owned by SoftBank, which is an investment fund that owns a lot of random businesses, including the somewhat now disastrous office space letting company, WeWork, whose value as well collapsed. I mean, not so long ago, SoftBank was attempting to sell ARM off in order to recoup a lot of the money that it had lost. And ARM was nearly swallowed up by Nvidia. Now, this, to be honest, would have caused a certain conflict of interest as Nvidia manufactures chips and based around its own design. And one of the main things about ARM, its appeal to other companies, is that it is independent. You're not essentially adding to a competitor's bottom line. If purchased by Nvidia, this would very much not be true and would imperil ARM's current business model. Now, eventually it seemed like the UK government was going to block that, but in the end I don't think it had to because Nvidia pulled out. So, ARM is still owned by SoftBank and, well, we'll see what happens on that front. This didn't happen acquisition by Nvidia may yet still have a lasting effect on ARM though, as when it seemed very much like this was going to happen and a certain amount of ARM's talent headed for the exit. Nvidia has a reputation of not being the greatest company in the world to work for, so quite a few of ARM staff saw the writing on the wall and left. And when you're a company that sells IP for a living, your talent is, well, that is what you are selling. that is your product. It's not like ARM has a lot of capital investment in plant and machinery that it's using. It just has essentially a back catalogue of design work that's been done, and what may be done by its staff in the future. So having an event where an amount of your talent leaves, well, that could be quite costly in the long run. Well, if you've made it to this point, I'd like to say thank you very much for watching. If you enjoyed this video, why not press the little button that YouTube has provided to indicate that fact below, or share it with other people you think might like it too. And if you'd really like to help the channel out, why not press that little subscribe button, and maybe even gently tickle the bell, as that has a huge effect on YouTube's algorithm and means that it will tell people that this video actually exists.